Okay, so I'm Alex Williams. I work for National Instruments as a software engineer. So one of the things that we're constantly pursuing is higher bandwidths. And it's starting to get rather difficult to move that data reliably to our systems. So one of the things that I've been working on and I've been studying is like, how do we move this data across in a faster fashion? And it turns out that a lot of our interactions with the kernel are kind of slowing us up. And so what I've done is taken a framework called DPDK, the Data Plane Development Kit, and used it to help accelerate our network processing with drivers and user space. So I should say that I work a lot with UHD, and so a lot of the examples and what I've done all pertains to it. But the challenges and the strategies for handling them kind of form design patterns that are common to other places. And so for like the GNU Radio scheduler, similar ideas will help out. So what I'll do first is I'll talk about how the usurp stream in network mode now and what's kind of limiting us. Then we'll talk about some technologies to help get around that. And we'll introduce DPDK, talk about the work that I've done, benchmark results, and the impact on GNU Radio. So how does UHD currently work? So basically, the architecture is kind of like this. You've got your radio right there. It's receiving its data over 10 gigabit Ethernet, and the application is sending it to the streamer APIs, which there's like a lower level one where we give it a transport, and we have to talk to the kernel to go over. Since transmissions are kind of bursty, we'll have a packet buffer to smooth that out, and the radio will consume it at kind of a constant rate. So how it works kind of in software then, to make this all kind of happen right. For TX, you'd have your buffer, you'd create your samples, you'd then maybe give your buffer over and wait for UHD to do its thing. UHD will take that buffer, will look to see, is there space in the packets, the buffer downstream, and if there is, I can send it out, I'll hand it off to the kernel, and finally it gets out. And there's a number of copies in there on its way to its destination. So it kind of takes a bit to get to where we need it to go. So in terms of like time and how things work, UHD, you need to keep in mind, uses credit-based flow control. So as we try to send packets down, we have to get a message back that says, okay, there's space, you can send more to the packet buffer. So in a way that this might work is you would at init kind of learn, okay, my buffer size is this much downstream. I can use this much of it. I'll send my command to start streaming sometime in the future. I'll fill the buffer, and then the radio can start streaming. And you'll see it kind of does it at a constant rate and just takes it out. Meanwhile, the radio and the packet buffer will send its flow control response. We'll handle it. It'll UHD will say, oh, okay, I can send more, there's more there, and hopefully it'll arrive in time so that we don't get an underrun. So with this, you can kind of see we need enough buffering to cover whatever is the worst case latency. Unfortunately, transmissions are kind of bursty, and we don't have complete control over the whole machine. So you can get a lot of jitter induced by the scheduler and other things that are happening at the time. And for example, this is kind of a cheesy one, but you could say, well, what if we got this flow control response and uh-oh, the OS needed to check for updates and we just can't do our thing. Well, what you see is we couldn't actually process that response in time, and then we couldn't send a packet until it was too late. We got our underflow, and then we had some junk send out over the radio. So one way to kind of help with this would be to say, well, okay, it's just need more buffers and need to fill it up more, but there's a cost to that. You end up with higher delays then all the time to get to your radio, and there's more hardware required. So let's take a little bit of a deeper look at, like, where's all of this coming from? What's happening with scheduling? So for a scheduler, you have like some set of tasks in a queue, and it'll be there trying to decide what should I run on all of these cores that I've got. And there's various metrics for talking about how it performs. There's fairness, which is like how equally am I sharing it, and then latency to like get to the end of your task. And threads can be pulled off a core in various ways. One of them would be voluntarily, where it just sort of needs to wait on something and it says, okay, I'm not running here, so something else can go there. Another one, though, might be involuntarily, where the scheduler maybe has a timer interrupt and says, yep, you're up. You can't run anymore. In both of those cases, though, you can end up with a situation where you don't get back on your core when you're ready, because you're waiting for that other thread. You're waiting for that other thread to come off first. And so there's always these delays then for your responses. So one thing to also keep in mind then is that Linux's default scheduler is the completely fair scheduler. So it's made to share a CPU core relatively fairly. They say completely fair, but that's not exactly true. And it doesn't really know what you're trying to do. It's kind of guessing. And as a result, your network activity, your processing, it might not understand that this needs to be high priority, and when the event comes in, it should schedule it right away. And that's kind of an explanation of why that thread that's waiting for the flow control response, it might then wait to get to it. On top of that, there can be issues where you have an application that creates a bunch of threads, but there aren't enough cores to handle it, like, say, Gnu Radio. UHD also actually creates a bunch of threads, too. And you can kind of see there a list of some of them that it has. And most of these spend their time sleeping, but they do have to wake up periodically and do their thing. And so every time you have another thread that needs to do something, it competes for that core time. And it also invites the scheduler to come in and say, I'm not going to let you run right now. Let's just let this other thing happen. And it doesn't know, okay, what's high priority? So again, the kernel defaults are just not optimized for real-time systems. Right here, this kind of gives you an idea of how well we do with the defaults that we've got and the usual kernel-based network stack. And you kind of see that we kind of hit roughly half of the best performance for like N320 for TX. So how can we do better? This can't really be all we can do, right? Well, there are various technologies out there that give us a way to inform the kernel that, of what it is we're trying to do and maybe take more control back from it. So there are ways to, a lot of them are called kernel bypass, but sometimes it's actually just a way to work together with what's there. So a strategy that we might have, okay, we have all this context switching happening because we're doing NIC transactions and it needs to go into BSD sockets and go into the kernel driver and share it all. Maybe we don't need to do that. Maybe we can take control of the NIC and just control it from our application and user space. Also, we could inform it of what's a high priority and what cores maybe we should use for certain things. And so there are actually APIs to do all of this. We have the Affinity Control APIs where you can say there's a mask that you have, you can run a particular thread on a core, and you can say nothing else should run on that. And then you have high priority scheduling classes. So anything in this class will run above anything that happens in the completely fair scheduler class. And so with those two together, you can effectively take control of CPU cores. There is another thing on top where you have like a boot argument and you can isolate a CPU where the mask only matches that one CPU, and that goes even further. So that helps us take control of scheduling. Then there's the drivers and user space part, and we have a few technologies here. One is the user space I/O, and with this you can make available like your device registers in user space. It can do DMA, you can receive interrupts. The only downside is that there aren't really any protections for where that DMA is going to. And so they came up with virtual function I/O, which then brings in an I/O MMU if your system supports it. And that will provide like page mappings so that you can't go to places that it shouldn't. And then there's VFIO for mediated devices. And this one's kind of special. It's for a case where you might have a device that you might want some of your control to still remain in the kernel, but maybe you want to give applications access to DMA engines. And that would be useful for if you have, say, multiple applications that are kind of trying to share a device, or if you have, you want to give out DMA engines to different VMs. That's specifically what that was actually made for. So if we combine all of these things together and get some secret sauce from Intel and Mellanox and some of the others, you come up with Data Plane Development Kit. And what this is sort of this networking framework for fast packet processing. It kind of provides a raw interface to all the network devices, so you don't get all the niceties like TCP and UDP and even ARP. That's all stuff that I had to implement. But it does mean that you get to make it as small as you need and have it do only the things that you want. On top of that, there are some other niceties. So they have some APIs to interact with those Affinity Control and real-time scheduling classes I mentioned earlier, and some other like data structures and memory managers and things of that sort to keep you from sleeping if that's what you want to do. And lastly, on that note, it is fairly widely supported. You do need a NIC that has a driver for it, but it's not hard to find. And the biggest ones are going to be Intel and Mellanox, but there's other vendors too on top of that. Okay, so then the work that I did on top is called UHDPK, but it no special name there. So you can see that with a conventional stack, you end up having just UHD there, and then there's a whole bunch that's implemented in the kernel before it gets to the network card. But for UHDPK, we have our driver and user space, and it's only for init just to set up your memory mappings that it goes to the kernel. The rest of the time, it goes directly to the network card, and you have much reduced latency. I did a little minimal network stack on top. It only supports exactly what we need, which is UDP and ARP and IP. And we had some zero copy operation where we would only pass along pointers to DMA-able buffers, and that cut out that copy that you would have between the kernel and your application. In terms of scheduling then, we had to come up with a better way to figure out how to show that our networking activity was high priority. And so we have a little threading model here where we can put certain ports on a configurable number of I/O threads, and then we'll assign I/O threads to specific cores, and that I/O thread will take it 100%. That CPU will never sleep. But as a consequence, you will be able to react to anything that comes in as fast as possible. And so this replaces sort of the UDP transport with kind of our Jitter streaming layered on top, and there were no changes at all to the Streamer API. You can use this with just a configuration file that describes the things that you would have in like Network Manager, because we can't use the system utilities to assign IP addresses anymore. We have to have it in our own configuration file, and a little device argument, and then it's right there and available to use, including your own configuration for which cores you want to actually use. And so performance, well, we achieved full rate streaming, 250 megasamples per second, 2 channels to each device, no problem. We ran a little bit of a test to show kind of what the difference was in the latency. So we measure this from the output of the RX port on the radio, going back to the device, and then sending a TX packet out and getting it measuring at the point on the TX part of the radio. And for using the kernel, that'd be about 300 microseconds. With DPDK, we reduced it all the way down to 80. And keep in mind that this is also going through the DDC and the DUC and a bunch of other blocks on its way there. So it gets much better. So for GNU Radio then, we'll add that on top. And performance improves, but it turns out GNU Radio has some bottlenecks. So for similar work, these are two different examples that are basically signal generators. You can see that we get kind of reduced performance for, so DX waveforms, sorry, I should say, is the example that's just UHD only. UHD SIGGEN is the one that uses GNU Radio to implement it with the SIG source block. What happens is it kind of gets reduced in performance because we end up making a ton of threads, and you get a lot of migration between cores. I think I'm previewing a slide here. Yeah. So the thread per block scheduler in particular may be a likely bottleneck. I know we've been talking about this a lot already during this conference, but it does replicate more threads than available CPU cores. We get kind of a lot of switching, a lot of threads moving around because it just assigns threads, the scheduler that is, assigns threads whenever a core is available. And then you end up with cold caches, cold like branch predictors, cold TLBs, all these sorts of things that then have to be loaded all over again. And then kind of funky, some of these blocks have really tiny workloads, and they still get their own threads. And all this frequent switching kind of just invites latency spikes. So what are the things we can do about it? Well, Marcus actually went over a lot of this already. But you know, we could partition the graph at a coarser granularity. Maybe let's not have so many threads. It's just not useful. And then we could take those subgraphs and put them on individual threads, assign them to cores, maybe do some pinning. There's some ability here to auto-adapt, but we should probably always have a way for the user to specify, because nobody knows the application better than the user themselves. And this question slide I had here, but I think it's become pretty clear as we've talked that, yes, we are interested in the higher data rates, and in terms of handling processing, GPUs and FPGAs and the whole heterogeneous computing thing is very important to us, and we'll keep working on it. So, any questions?
So is this something I can download now? It's available now, and if so, are there application notes or something on how I can implement it into UHD on my machine?
Yep, it's all open source. It's been in 3.14 since it was released, I think 3.14.0, when we released in 3.20. And it's in our manual and on our knowledge base.
So I've been playing around with DPDK myself. Is that actually true? You can't have an I/O thread that is not consuming a full CPU core, because at low rates, obviously, that's kind of a waste, right?
Right. So that's why it's an option, because you might not want to use it for your low rate thing. This is more for a high rate case where you know you're going to have data constantly coming in, so there's no reason to switch out. In a similar case, you might want to have options for the GNU Radio scheduler where maybe sometimes you want to have switching, sometimes you don't, because maybe power is more important than being constantly ready.
The other question I have is the log-free ring exchange buffer, right? Mm-hmm. Is that your creation, or does that come with DPDK or whatever thread building blocks?
That particular one was a creation from DPDK. And then I added some wait queues and such to deal with timeouts.
Oh, cool, thanks.
Did you find any influence from the Spectre or Meltdown mitigations implemented in the kernel in the last year?
Did I see anything with the mitigations?
So especially regarding task switching, you find a lot of reduced power if you have to do a context switch and such stuff.
Right. So I imagine that would make the UDP or the kernel case even worse than it is now. So then that would be another argument to use DPDK because you do less of the context switching. But I haven't specifically looked at what the impact is there. Thank you.